Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we're going to be talking about angle side theorems. Okay, these are very cool theorems, very powerful theorems, and I think you're going to have a good time with it. All right, number one, base angle theorem. The base angle theorem simply states that if two sides of a triangle are congruent, then the angles opposite the sides are congruent. The shorthand would be if leg is congruent, comma, then base angles congruent. Or if the legs in the triangle are congruent, then the base angles are congruent. You can use either one of these if you like. Please notice that the inverse of this theorem is also true. In other words, remember that the inverse negates the conditional. So the inverse would be if two sides of a triangle are not congruent, then the angles opposite those sides are not congruent. The converse of the base angle theorem. Remember, the converse just switches the if and the then part. So therefore, if two angles of a triangle are congruent, then the sides opposite the angles are congruent. Again, the shorthand would be if base angles congruent, then legs congruent, or if the base angles of a triangle are congruent, then the sides are congruent. Okay? Please notice as well that the inverse of this theorem is true as well. In other words, if two angles of a triangle are not congruent, then the sides of those angles, the sides opposite of those angles are not congruent. Okay. So using the theorems mentioned above, we can now prove that a triangle is isosceles in the following two ways. Number one, if at least two sides of a triangle are congruent, then the triangle is isosceles. And number two, if at least two angles of a triangle are congruent, then the triangle is isosceles. Visually, we could state if the sides of two triangles, or in other words, the legs, are congruent, then the triangle is isosceles. Or if the base angles of a triangle are congruent, then the triangle is isosceles. So two very, very powerful theorems here. All right. Side angle theorem. The side angle theorem states that if two sides of a triangle are not congruent, then the angles opposite them are not congruent, and the larger angle is opposite the longer side. Let me repeat that. If two sides of a triangle are not congruent, then the angles opposite them are not congruent, and the larger angle is opposite the longer side. The angle side theorem is very similar. It states that if two angles of a triangle are not congruent, then the sides opposite them are not congruent, and the longer side is opposite the larger angle. Now, what does that mean? This figure helps you out. In other words, what this is saying is that the larger angle is always opposite the longer side and vice versa. The longer side of a triangle is always opposite of the larger angle. The middle, or the second largest angle, is always opposite the second largest side, and the opposite is true as well. The second longest side is opposite the second largest angle. And last but not least, the smallest angle is always opposite the smallest side, and the opposite is true as well. The smallest side is always opposite the smallest angle. So as you can see, angle 100 is the largest angle, and that is opposite the longest side of 12. Okay? 100 goes to 12. The second largest angle, which is 50, is opposite the second longest side, which is 11. And the smallest angle, which is 30, is opposite the smallest side, which is 9. Very good stuff here. Very powerful. That's all we have to learn today, so let's get to the examples. But before we do, I did want to mention that using both the angle side and side angle theorems, it is easy to understand why equilateral triangles are also equal angular triangles. Okay? If I have an equilateral triangle, okay, let's call this ABC, and I know that it's equilateral, that means that all the sides are congruent, then using the angle side and side angle theorems, it's easy to see, well, if all these sides are congruent, then that means the opposite sides, the opposite angles to those sides must also be congruent. And since there are 180 degrees in a triangle, each angle must be 60 degrees. Okay, we learned that last lesson, but now hopefully you can really understand why because of these theorems. So let's put this into action. Here I am given that side or segment AC is greater than segment AB. The measure of angle B plus the measure of angle C is less than 180 degrees. Angle B, or the measure of angle B, is 6x minus 45 degrees, and the measure of angle C is 15 plus x degrees. I want to find out what are the restrictions on the values of x. Well, this is a pretty fun problem. Since we know that AC is greater than AB, then that means that angle B must be greater than angle C. So what does that mean? That means that angle B, which is 6x minus 45 degrees, must be greater than 15 plus x degrees, which is angle C. So let's go ahead and solve it. This is a very easy equation to solve. We're going to add 45 to both sides, giving me 6x is greater than 60 plus x. Subtract x to both sides, giving me that 5x is greater than 60. And when I divide 5 to both sides, I know that x must be greater than 12. Okay? And since angle, the measure of angle B rather, plus the measure of angle C is less than 180 degrees, we can also figure the following. Since the measure of angle B is 6x minus 45 plus the measure of angle C, which is 15 plus x, that is less than 180. Let's go ahead and solve for x. Combine like terms. 6x plus x is 7x. Negative 45 plus 15 is negative 30. That is less than 180 degrees. add 30 to both sides. That gives me that 7x is less than 210 divided by 7. X would be less than 30. So therefore, x must be greater than 12, but less than 30. And bingo, we got our restrictions of x, which is what I was looking for from the beginning. Okay? Hopefully that made sense. I thought that was pretty fun. All right, now the real fun part, your favorite part, proofs. For example 2, we have this triangle JOM, which is isosceles with angle JOM as the vertex angle. We're also given that OK, or ray OK, bisects angle JOM. I want to prove that segment OK is the median to the base. And remember, if JOM is the vertex, the base is always opposite the vertex, so the base here is JM. So I'm trying to prove that OK is the median to base JM. So that means we're going to have to prove somehow that JK is congruent to KM. All right? Now what I did here, because it's a long proof, I went ahead and redrew the figure here so we can easily see how the proof works. Okay, number 1. I know that triangle JOM is isosceles with angle JOM as the vertex. That's a given. Number 2, since we know that triangle JOM is isosceles with angle JOM as the vertex angle, then that has to mean that OJ must be congruent to OM. Why? Definition of an isosceles triangle. We know that isosceles triangles have base angles and legs that are congruent. Number 3, they tell us that ray OK bisects angle JOM. That's a given. Well, if OK bisects angle JOM, then we know very easily that angle JOK must be congruent to angle MOK because of definition of angle bisector. Now looking at this triangle here and remembering what we're trying to prove, we're trying to prove that JK is congruent to KM, so we can prove that OK is the median to the base. So with that in mind, we can say that OK is congruent to OK because of the reflexive property. Now look at the triangle that we have and look at our tick marks. Now it's very easy to state that triangle JOK, this guy right here, is congruent to triangle MOK, which is this guy right here, because of side, angle, side. Since I know that these two triangles are congruent, now I can state that JK is congruent to MK, which is what I wanted to prove because of CP/CTC. And now that I've proven that JK is congruent to KM, well, we know now that OK is the median to the base. Why? Definition of a median. If you remember, a median is a segment that starts at the vertex of one angle and cuts the opposite side, which in this case is base JM, into congruent halves. And we prove that. Done. That was a nice proof. Okay, Number 3, we're given that angle 3 is congruent to angle 4. We're given that BX is congruent to AY, and we're given that BW is congruent to AZ. I want to prove that triangle WTZ is isosceles. All right, it's kind of a long proof as well. So what I did was, once again, I redrew the triangle here right with the proof so we could see how it links up in an easier fashion. Number 1, angle 3 is congruent to angle 4. That means right here, angle 3, okay, is congruent to angle 4. Please note that angle 3 is this guy right here, and angle 4 is this guy right here, okay? Since we know that angle 3 is congruent to angle 4, take a look at angle WBT. Doesn't this angle form a straight angle? And look also at angle TAZ. Doesn't that angle form a straight angle? Okay, so since that is true, we can assume that those are straight angles. We can state that angle 3 is supplementary to angle WBX. So it's supplementary to this angle right here. And why? Because of the definition of supplementary angles. On the other side, we can also prove that angle 4 is supplementary to angle YAZ, which is this angle right here, because also definition of supplementary angles. Now we can easily prove that angle WBX, this angle right here, is congruent to angle YAZ, which is this angle right here. Why? Because supplements of congruent angles are congruent. Since angle WBX and angle YAZ were supplementary to 3 and 4, which are congruent, that means that angle WBX must be congruent to angle YAZ. All right, so let's continue. We were also given that BX is congruent to AY. Okay? BX, which is this guy right here, is congruent to AY. We were also given that BW is congruent to AZ. So that means that BW is congruent to AZ. Those were both given to us. Now we can really focus on the two little triangles that we have here, triangle BX or BWX and AZY, and we can prove that triangle BWX, which is this guy right here, I'll do it in red, is congruent to triangle AZY, which is this guy right here in blue, because of side, angle, side. Since we've proven that those two triangles are congruent, we can also now state that angle W, I'll do this with 3 lines, is congruent to angle Z, I'll do this with 3 lines as well, because of CPCTC. Now look at the grand picture here. In this whole triangle here, WTZ, my base angles now are congruent. So therefore, I know that my large triangle outlined in black here, triangle WTZ, is isosceles. Why? Definition of isosceles triangles. Okay, should have added a little triangle here. I apologize. All right? And why? Because an isosceles triangle has base angles that are equal, which we have proven. All right? Okay, hopefully that made sense to you as well. Now, last but definitely not least, example 4. I have that angle E is congruent to angle H. I have that segment EF is congruent to segment GH. And I'm trying to prove that side or segment DF is congruent to segment DG. Again, I want to make the proof very easy for you to understand, so I drew the figure again to the right of our statement and reason columns. Number 1, angle E is congruent to angle H. That's a given. So angle E is congruent to angle H. Right off the bat, that should indicate to you, hey, wait a second. These base angles are equal. That means that this triangle EDF, or EDH rather, I'm sorry, EDH, the triangle I just outlined in red, has to be isosceles. And if it's isosceles, then I know for sure that segment DE must be congruent to segment DH. Why? Well, this is the base angles theorem, or rather the converse of the base angles theorem. If the base angles of a triangle are congruent, then the opposite sides of those base angles, or in other words, the legs, are congruent. Number 3, they tell you that EF is congruent to GH. That is a given. And now, look at what we have here. We can now easily see that if I just connect DF here and DG, that triangle DEF is congruent to triangle DHG. But again, DEF here in green must be congruent to triangle DHG, this triangle here in blue. Why are they congruent? Because of side, angle, side. And therefore, if those two triangles are congruent, then our final conclusion, DF must be congruent to DG because of CP/CTC. Corresponding parts of congruent triangles are congruent. Well, that does it. I hope you learned a lot. Thank you very much, and have a wonderful day. Bye-bye.